everyone, and welcome to the lecture on conjugated pi systems and pericyclic reactions. Okay, so we're going to start off by talking about the different classes of dienes. We have three types of dienes: accumulated, conjugated, and isolated. Isolated dienes are like separate alkenes. They have one or more sp3 hybridized carbons in between, and so any p orbitals on these two carbons don't have any ability to overlap with p orbitals on those two carbons. So those would react similarly to the way alkenes react. There's also accumulated pi bonds where they share a central carbon. This works with the carbon in the center being sp hybridized. The pi bonds are actually isolated because the p orbitals overlap in such a way where one set of p orbitals goes, let's say, in a vertical direction, and the other set of p orbitals would overlap 90 degrees or orthogonal to those. So there's no overlap between the p orbitals on each set of pi bonds, so they in a way also would react like an isolated pi bond. And we're not going to talk about those any further in this course. This chapter really focuses on conjugated dienes. Conjugated dienes have one single bond in between the two pi bonds. And we're going to talk about them because they're more stable than isolated or accumulated dienes, and they have unique reactivity. If you want to look at the p orbitals for the different types of dienes, you can see the isolated p orbitals are just regular pi bonds. This is an example of what the pi bonds would look like in an accumulated system. And then the conjugated system is special because all four p orbitals, if they're all in the same plane, they can align. So there's greater electron freedom and delocalization, which leads to greater stability. As I mentioned, the chapter focuses on conjugated systems, and it's important to note that all four atoms don't have to be carbon. For example, this is a conjugated diene, but it's called something a little bit different than a diene because of the presence of an heteroatom, which is an atom other than carbon, as part of the system with the overlapping p orbitals. Because it's a carbonyl, which could be called a ketone, this would be a conjugated enone. Ene taking into account the alkene and the one taking into account the ketone. However, this is a conjugated pi system, just the same way conjugated dienes are. We want to think about how do we synthesize conjugated dienes. For example, 1,3-butadiene, which is shown here. We can synthesize them through the way we would synthesize pi bonds, through elimination. So for example, we can use a bulky base to do an E2 reaction on this allylic bromide system. One of the reasons why a bulky base is used is to prevent any SN2 reaction from occurring, and also to, if there was any issue of regioselectivity, we would want to make sure that a less sterically hindered proton on a terminal carbon could be abstracted, and preferentially, and that would work well with a bulky base. From a geminal dibromide, we can do a double elimination also to get the 1,3-butadiene. Let's talk about the single bond. So we mentioned that there's pi bonds, and in between there's a single bond. But the single bond is a little bit different than traditional carbon-carbon single bonds, in that if you measure the bond distance, it's a little bit shorter than a typical carbon-carbon single bond. There's a few reasons that can be attributed to. The first is due to the overlap of sp2 to sp2 hybridized orbitals on these two carbons versus sp3. So these two carbons are sp3, which means that they use sp3 hybridized orbitals. And the shape of sp3 hybridized orbitals is more elongated, leading to a longer bond. These two carbons hybridized to sp2 hybridized orbitals being a little shorter, they two nucleuses get a little bit closer together with the same amount of orbital overlap. Again, if you want to remind yourself of what the shape of your orbitals looks like, a p orbital is a perfect dumbbell, and an s orbital spherical, and then the hybridized orbitals are shown in between. Recall that an sp2 hybridized orbital with greater amount of s character, specifically about 1/3 s character, it will be more closely resembling an s orbital than a p orbital, compared to an sp3 hybridized orbital that's only 25% s character. As a result of the shape of the orbital, to get the same amount of orbital overlap when two sp2 hybridized orbitals overlap in a head-to-head fashion, the nucleuses of the two atoms end up getting closer together than when two sp3 hybridized orbitals do a head-to-head overlap. So that can at least partially attribute to the different length of the carbon-carbon single bond. There'll be another reason that we talk about eventually once we get into molecular orbital theory. For now, let's talk about the stability of conjugated dienes. Well, one study we can do to look at stability is a heat of combustion or a heat of hydrogenation study. In the case where we can reduce pi bonds, it makes sense to do a heat of hydrogenation study. Or we can look at the reduction of 2 moles of one butene with 2 moles of hydrogen gas and see how much energy that gives off when it's hydrogenated to butane. And that looks like about 254 kilojoules. When we hydrogenate 1 mole of 1,3-butadiene with 2 moles of hydrogen gas, we only get 238 kilojoules of energy released. So that means that there's a difference in 15 kilojoules when you're looking at conjugated dienes versus isolated dienes. Because obviously if you're using one butene, it can't be conjugated since there's only 1 pi bond. But there's 2 pi bonds total since we're looking at 2 moles. So that means that when you have 2 pi bonds in conjugation with one another, they're about 15 kilojoules more stable than isolated diene. Think about what else you know about the stability of dienes when you're answering this question. Compare the following 3 isomeric dienes. Which compound would liberate the least heat upon hydrogenation with 2 moles of hydrogen gas? Which would liberate the most? Go ahead and think about it, pause the video, and when you're ready, we'll go over it. Okay, so let's go ahead and go over it. So it looks like, in terms of the dienes, I can see that this one is conjugated because there's only 1 single bond in between the 2 pi bonds, but both of these are isolated. That's going to give me my first clue. And then between the two, I want to think about which one might be more stable. Well, another thing that I know about the stability of alkenes is that the more substituted the alkene, the more stable. So when we're looking at the alkenes, we're going to look at the carbons that are sp2 and ask ourselves how many non-hydrogen-based groups are attached. So here we have 1, 2 hydrogens that don't count, and then 3. So there's a total of tri-substitution over the 2 pi bonds. When I look at these, I notice that overall I have more substitution. This is the same, 1, 2, but this one also has these as well, and this third one. So I really have 1, 2, 3, 4, 5, right? So I have 5 carbons attached total over the 2 pi bonds. So because I have greater substitution between the 2 isolated dienes, this one should be more stable. Okay, then call this A, B, and C. More stable than A. Okay, so in terms of stability, I can definitely say that the conjugated one should be the most stable, right? Followed by the second most stable, and then the least stable. But that's not enough to answer the question, right? The question actually asks which compound would liberate the least heat upon hydrogenation, and which one would liberate the most. So you need to think about an energy diagram when you're thinking about the answer to that question. Right? If we're labeling these to eventually hydrogenate to the same place, which would be ethyl cyclohexane, which one is lower energy or more stable, and which one is higher energy or less stable? Right? So the least stable is actually going to be the highest energy. So I'm going to place that higher on the graph. The most stable will be the lowest energy. And then intermediate to that would be sort of in between, right? So I've got these three energy levels, and they're all sort of hydrogenating, giving off energy to get to the same product. So when we're asked which one would liberate the least heat upon hydrogenation, the answer to that one would be B, right? We have the least heat liberated. And the least stable would actually release the most heat or energy upon hydrogenation. Okay, moving on, I want to talk a little bit more about conjugated dienes. And let's talk about what we know about sigma bonds already. One of the things we know is that sigma bonds freely rotate, whereas pi bonds have restricted rotation, because if we rotate a pi bond, we'll lose the overlap of the p orbitals. So if we expect that sigma bonds can freely rotate, then we would expect that we can rotate around this single bond to get to two different conformations. And that's exactly true. We can rotate between these two conformations. However, they're not necessarily equally stable. We're going to differentiate or name these conformations S-cis and S-trans. The S stands for the single bond. So we're talking about the cis and trans with respect to the single bond in the center. Now, of course, we don't normally think about cis and trans isomers being related to a single bond. And that's why it's a little bit different than the normal classification or use of the terms cis and trans. So what this is saying is that with respect to the single bond, the two pi bonds are on the same side. That's kind of like a cis conformation. So with respect to the single bond, we'll call this S-cis. When the two pi bonds are on opposite sides of the single bond, that conformation will be called S-trans. To be very clear, there are no cis or trans double bonds in 1,3-butadiene. We're just talking about different conformations with respect to a single bond. So it's a little bit different use of the terms here. These two conformations are actually the most stable of the conformations of 1,3-butadiene. And that's because when all four atoms are planar, whether they're in a cis or S-trans conformation, all four p orbitals on those four carbons are in the same plane, and therefore they can all overlap. And when you have additional overlap of the interior p orbitals, recall that stabilizes the molecule. There are many other conformations as we rotate around this single bond where they're not in the same plane. Therefore, we would not have quite as much orbital overlap. And those would represent less stable conformations of the same structure. So because there's two different conformations and they can go back and forth, kind of think of it as like two cheer conformations, right, where we rotate different bonds to get from one conformation to the other, we can draw an energy diagram where we look at the conversion of 1,3-butadiene from its S-cis conformation to its S-trans conformation. Notice that the S-trans conformation is more stable than the S-cis conformation, and that's due to steric hindrance. If you draw in the hydrogen atoms attached to the terminal carbons, there's one hydrogen pointing in here as well as one pointing out, and one hydrogen pointing in here as well as one pointing out. The two that point in on the S-cis conformation actually run into each other in terms of utilizing the same space. So that creates a little bit of a strain that makes the S-cis conformation a little bit less stable or higher in energy than the S-trans conformation. Notice that it goes through a transition state that is 15 kilojoules per mole higher in energy than the two most stable conformations for the molecule. At this point, there's no overlap between the interior p orbitals, and eventually we'll be able to see a picture of what the p orbitals look like at that transition state. So here is that picture I talked about where we're rotating the single bond, and we have essentially rotated it 90 degrees, where the p orbitals are no longer in the same plane. Instead, they're actually orthogonal to one another, and there's absolutely no overlap between these interior p orbitals. So at that point, they're like isolated pi bonds because there's no overlap or communication between these p orbitals. And so it makes sense that it's 15 kilojoules per mole barrier because we know that's the stabilization energy of conjugating pi bonds. Let's review molecular orbital theory. We need to review sort of simple molecular orbital theory that was discussed last semester because it's the first time we're talking about molecular orbital theory this semester. And then we'll move on to more complicated conjugated pi systems. So in review, molecular orbital theory is one of the two bonding theories. And it's the theory, both theories have predictive capability, right? But molecular orbital theory talks about the combination of wave functions that are associated with atomic orbitals. So we're going to be reviewing molecular orbital theory of pi bonds. Molecular orbital theory also applies to sigma bonds, but because we're looking at conjugated pi systems in this chapter, it's going to be more beneficial for us to talk about molecular orbital theory as it applies to pi bonds. So molecular orbital theory says when two p orbitals, in this case, because we're talking about pi bonds, when two orbitals, in this case p orbitals, overlap, their atomic wave functions combine to form new wave functions. So these would be the atomic p orbitals, and these are pictures of the new molecular orbitals. And molecular orbital theory says the number of atomic orbitals that combine, that equals the number of molecular orbitals that are formed. So since we're overlapping two p orbitals, we're forming two molecular orbitals. The molecular orbitals extend over the entire molecule. So it basically means that the atomic orbitals cease to exist and form molecular orbitals. The lowest energy molecular orbital extends over the entire 2-carbon system, and electrons have freedom in that space. The two molecular orbitals that are formed are not the same in energy. One is a lower energy called bonding molecular orbital. In this case, because it's a pi bond, we're going to call it a pi bonding molecular orbital. And there's also a pi anti-bonding molecular orbital that's higher in energy. So this would be the energy of the atomic 2p orbitals. When they combine to form molecular orbitals, we have a lower energy bonding and a higher energy anti-bonding molecular orbital. Each p orbital brings one electron to the bond. So both of these two electrons will pair up and occupy the bonding molecular orbital. And the anti-bonding molecular orbital does not have any electrons in it. One of the things that differentiates the bonding and anti-bonding molecular orbital is the presence of nodes. Nodes are regions where there's zero probability of finding electron density. So in the bottom case, there are no nodes, and that's always going to be true of the lowest energy bonding molecular orbital. As we move up in energy, there's one more node, and if there were more than 2 molecular orbitals, the next highest energy molecular orbital would have 2 nodes, and then 3, and so on. Let's look at another system. Instead of looking at just a simple pi bond, where we're overlapping 2 atomic p orbitals, what about a conjugated diene in 1,3-butadiene? That has 4 p orbitals, 1 for each carbon, and if they're all planar, then they all overlap. And when they overlap, they form molecular orbitals. And because we're combining 4 p orbitals, we're forming 4 molecular orbitals. The 2 lowest energy are both lower in energy than the p orbitals, so they're considered bonding molecular orbitals. And the 2 highest energy are considered anti-bonding because they're higher in energy than the atomic orbitals that formed them. Notice as we look at the lowest energy bonding molecular orbital, there are no nodes. As we move up, we increase the number of nodes by 1 each time. Each p orbital brings 1 electron to form the pi bonds. That means that there's a total of 4 electrons coming from the 4 p orbitals. So we'll place 2 of the electrons in the lowest energy bonding molecular orbital and 2 in the next lowest energy also bonding molecular orbital, which means that 2 electrons have the freedom to roam over all 4 atoms. But the other 2 electrons are sort of separated on each side of the 4-atom system with a node in the center, which means that there's a change in sign on either side of the node, and there can be no constructive overlap between these 2 molecular orbital locations. And as a result, there is some single bond character between these 2 carbons and some double bond character between the 2 carbons as well. So again, because of these 2 electrons, there's some double bond character between these 2 carbons, right? But there's also single bond character because we have 2 electrons that don't have as much freedom. And as a result, there's no, quote, pi bond character attributed to this molecular orbital. So this is what we were talking about, this out of phase, non-constructive overlap in the second highest energy bonding molecular orbital. So this leads to some single bond character and some double bond character. So this central carbon-carbon bond doesn't really have as much pi bond character as the terminal carbon-carbon bonds. So that's why that's one reason why there's some molecular freedom, right? If all 4 electrons could occupy and go over the entire system and there was double bond character equally amongst all 3 carbon-carbon bonds, we would expect that we would not be able to rotate this central carbon-carbon bond, but we can rotate it. And the molecular orbital theory helps us understand why, because there's not completely double bond character between that carbon-carbon bond, the way there is between the terminal carbon-carbon bonds. Let's look at another system. In this case, we have 1,3,5 hexatriene. So as we increase the number of pi bonds that are in conjugation, then we have the opportunity to have an additional amount of p orbitals overlapping. This system has 6 overlapping p orbitals, which means molecular orbital theory tells us that we should form 6 new molecular orbitals. 3 will be bonding and 3 will be anti-bonding. And the lowest 3 bonding orbitals are all filled with electrons. There's some important terms that we want to know, and those terms are the HOMO and LUMO. And HOMO stands for the highest occupied molecular orbital. So it's the molecular orbital that's the highest energy that's occupied with electrons, right? So these 2 are lower in energy. This is the highest energy a molecular orbital that actually has electron in it, so we're going to call this the HOMO. This is the LUMO, and it stands for the lowest unoccupied molecular orbital. And it's the orbital that has that's the lowest energy that has no electron density. So these are important molecular orbitals because the HOMO and LUMO are involved in reactions. And together they're termed the frontier orbitals. They're termed the frontier orbitals because it's where the chemistry is happening. And so it's the orbitals that we really want to look at when we're trying to understand reactions. Frontier orbital theory was first advanced in 1954 by Kenichi Fukui, and he was a co-recipient of the Nobel Prize in Chemistry in 1981. So this is a really important theory that has a lot of predictive capability of a bunch of different reactions. And one thing that we want to note about the HOMO and LUMO is that if we shine light on a conjugated pi system, an electron can be promoted from the HOMO to the LUMO, and in that case, the HOMO and LUMO change because now this is the highest occupied molecular orbital. Right, so the highest energy orbital that's occupied by at least one electron, which makes this the new LUMO. And this is going to become important as we start to talk about reactions that might be possible when light is introduced to the reaction. And by the way, this sort of light promotion happens when you have extended conjugated pi systems, because the higher the amount of conjugation, the closer in energy the HOMO and LUMO get, and the more feasible it is to promote an electron from the HOMO to the LUMO. And that will be discussed more in lab when we talk about how conjugation affects color, and we're going to talk about UV spectroscopy and other things related to light, like chemiluminescence and other factors. So look for more discussion of how conjugation affects other factors in lab. Okay, let's start talking about electrophilic addition. So recall from either chapter 8 or chapter 9, depending on the book edition that you're using. Last semester, when we talked about addition reactions of alkenes, if we have an alkene, the pi bond will react with HBr. The first step is proton transfer, leading to the more stable carbocation. And then bromide will do a nucleophilic attack, leading to the addition of H and Br overall. So the addition of HBr, and this would be a Markovnikov addition of those two. So we call this a Markovnikov hydrohalogenation reaction. So let's look at what happens if instead of using an alkene, we use a conjugated diene, and we treat that with HBr. What actually happens is we end up getting a mixture of products. The products are related as constitutional isomers, and there is going to be a major and a minor product, and it's temperature dependent. Let's look at the mechanism involved. The mechanism starts off in a similar way as when there's just an alkene reacting with HBr. The first step is proton transfer. So one of the pi bonds will act as a base to pick up a proton from HBr, generating bromide and a carbocation. If you ask yourself, does it make sense that the carbocation goes on the terminal carbon or the interior carbon? When you draw those two out, it becomes clear that the terminal carbon would be a primary carbocation, which is too unstable to form. In addition, the alternate option is placing it on the internal carbon, which actually makes for an allylic carbocation. Allylic carbocations are resonance stabilized. So an allylic carbocation is by far more stable than a primary carbocation. In fact, primary carbocations that are not resonance stabilized are so unstable that they don't form. So the proton transfer step is considered regioselective, where we form the more stable or substituted allylic carbocation. So once the carbocation is formed and we see that it exists as there's two resonance contributors, so the true structure is a hybrid of those two structures, you see that the positive charge is not localized on one carbon, but instead delocalized over two different carbons. So each of these carbons actually shares the positive charge or has a partial positive charge. But because they both have a partial positive charge, they are both electrophilic and can be attacked through a nucleophilic attack by bromine or bromide. And because bromide is attacking two different carbons, we end up with two different products. Sometimes people name these products and they call this the product that's the result of 1,2 addition versus this product, which is the result of what's called 1,4 addition. That comes from, if you were to number the carbons, for example, 1, 2, the hydrogen and the bromine are getting added on adjacent carbons or carbons 1, 2. If we start counting where the hydrogen was added and we count to where the bromine was added in the second product, it looks like they're on carbons 1 and 4. That's where the term 1,4 addition comes from. So you may be asking, again, which one is the major product? Well, actually, it depends on the temperature because one of the products is more stable and the other product forms faster. Let's do a practice problem before we talk about the major product any further and just predict the products, of the following reaction and propose a mechanism that explains the formation of each product. Go ahead and pause the video and then we'll discuss it when you're ready. Okay, let's go ahead and go over this. So it would like a mechanism and it would like for us to show both products. So let's start off with the mechanism and then we can figure out the product. Maybe there's more than two products. We're going to analyze and figure it out. Okay, first of all, one of the things that's different from the previous example is that this diene is not symmetrical. So there is no internal plane of symmetry, which means that protonation at this terminal carbon leads to a different intermediate than protonation at this terminal carbon. So we're going to need to consider both. So if we have proton transfer from the top pi bond and draw out proton transfer from the bottom pi bond, we'll be able to analyze them simultaneously. I'm going to use the top pi bond to show proton transfer and the bottom pi bond. Recall that we already decided that it makes sense to show the proton going on the terminal carbons, because that leads to an allylic carbocation intermediate. The hydrogen is going to either end up on one terminal carbon or the other. The carbocation ends up on the other carbon that was participating in the pi bond that did the nucleophilic attack. Or sorry, the proton transfer. Okay, both of these are allylic carbocations. So we want to draw out the resonance stabilization. Don't forget when you're drawing resonance contributors, show your double-sided resonance arrow. We are going to do the allylic carbocation pattern, which shifts the pi bond over. Okay, so we finished off drawing the resonance contributors, so we can see where the positive charge is located. We also formed some bromide in the first step. Since we have 4 entirely different structures here, of course, it's only 2 different intermediates because this is together makes up one compound and another compound here. We can show nucleophilic attack. So the bromide can attack anywhere there is a positive charge. So we can, instead of drawing it 4 times, I'll just draw it attacking and then just say giant 4, attacking essentially all of those places. That's going to lead to now different products. So let's go ahead and draw out what those products will look like, and we'll determine if any of them are the same or if they're all different. At this point, I'm going to go ahead and you have to draw in the hydrogen. It's just there for clarity. If you want to continue adding it, you can. And maybe just for clarity, I'll go ahead and continue adding it, just to make sure that everybody is understanding where the 1, 2, and 1, 4 addition labels come from at the end. Okay, so I went ahead and drew all of the different products, and now I'm going to look at comparing them to see if any of them are the same. So when we look, we see a bromine followed by pi bond, the methyl, right? You can kind of ignore this hydrogen. Sometimes it's not even drawn in. So ask yourself, is that the same as any of these other structures? Looks like it is not the same as this one because it's too close to the methyl here. Same thing with that one. And it's not at the tertiary carbon. So this is a unique product, right? And let's look and see if this is the same as any of the others. Ignore this. This is a bromine at the tertiary carbon. None of the other ones are showing that. That's also a unique product. And then we have bromine next to the carbon with the methyl. So these look like actually the same product to me. So 3 different products formed here. Sorry for the interruption there. Right back. So we're going to label these as same. Right, so there's really 3 different products. Okay, going back to the slides. A short break to mention that in addition to adding HBr across the diene, we can also add Br2. When we add Br2, we're adding 2 bromines that will either add 1, 2 or 1, 4. So the reaction works the same way as with HBr, when we use Br2. Okay, let's continue and talk about which one would be the major product. Right, so this is the regioselectivity issue of this problem or this reaction. So it turns out, as I mentioned before, it's actually temperature dependent. So at lower temperature, it looks like in this particular example, the 1,2 adduct is the major product, but at higher temperature, the 1,4 adduct in this particular example is the major product. To understand why we would get a different major product at different temperatures, we need to look at an energy diagram. So the first step is shared between the two pathways. You have the proton transfer step leading to the allylic carbocation and bromide being formed. At this point, there's a difference in the product when bromide attacks either one of the central carbons or the terminal carbon. And remember, since this is allylic, here the carbocation is not actually located in one carbon, but shared amongst the two carbons. And the 1,2 adduct looks like the faster pathway with a lower activation energy. And the 1,4 adduct looks like it is a slower pathway, but forms the more stable product. So when we have a difference where you can form two different products, and one is formed faster, but the other one is more stable, then we have a situation where it can be temperature dependent in terms of predicting the major product. The faster pathway with the lower activation energy, we call this the kinetically favored pathway. And the more stable product is the thermodynamically favored product. And let's look at the reaction a little bit more to understand why one pathway might be faster and one might be more favored in terms of the stability of the product. Okay, so the 1,4 adduct is actually more stable. And we can tell that because we're forming a disubstituted alkene versus a monosubstituted alkene. The 1,4 adduct is more substituted, and we know that more substituted alkenes are more stable. So it makes sense to show this as the lower energy or more stable product. At higher temperatures, the products are equilibrating, and the reaction is said to be under thermodynamic control. And the product that is more stable will be the major product. Let's go back and look at that energy diagram to understand what that means. What does it mean that the products are equilibrating? And why does that happen at higher temperature? Well, initially, more molecules will undergo the blue pathway because it requires a lower activation energy, and a higher percentage of molecules will have enough energy to overcome that activation energy barrier. So initially, more of the 1,2 adduct is formed in solution. However, at higher temperature, there's enough energy that the reaction or this particular step is reversible. And if both pathways are reversible, eventually we can reach an equilibrium, and the major product at equilibrium will be the more stable product. What about the 1,2 adduct? Why did we say that it forms faster? This is considered to be due to what's called the proximity effect. So if we look at that first step again, the proton transfer, where we end up with the allylic carbocation, the proton is delivered to carbon number 1. Well, bromide, which just got separated from the proton in HBr, is right next to carbon number 2 after it delivers a hydrogen or a proton to carbon number 1. Therefore, it is in closer proximity to carbon number 2, and it can essentially attack there faster than it can attack carbon number 4. So this proximity effect of the ions and their attraction leads to the formation of the actually less stable product to occur faster. And the reaction at low temperature is said to be under kinetic control, because at low temperature, we're going to favor whatever forms faster, because the reverse of that second step is not as likely at low temperature. Because if we go back to the energy diagram, what we'll see is that initially we form more 1,2 adduct, but if we don't have enough energy, it's unlikely that the step is as reversible because the activation energy to go back is a lot higher than it was to go forward. So we essentially trap whatever product forms faster at lower temperature, and we don't allow the products to equilibrate. So what I want to say before we do any more practice problems is just to make it really clear. The 1,2 adduct is always the kinetic adduct, and it's always the major product as a result when the reaction is done at lower temperature. The more stable alkene is the thermodynamic product, which is not always the 1,4 adduct. It's whichever adduct has a more substituted alkene. So I want you to make sure that you write down in your notes, the 1,2 adduct is always the kinetic adduct, but the 1,4 adduct is not always the thermodynamic adduct. It's whatever adduct is more substituted will be the thermodynamic adduct. So that's something to keep in mind as we do some practice problems. And I think we're going to be doing a couple of practice problems in a row here. Let's look at the first one. We're going to look at this now symmetrical conjugated diene to predict the products for the following reaction and determine which product would predominate at 0 degrees versus 40 degrees. Go ahead and pause the video and resume when you're ready. Right, let's go over the problem. So since it's symmetrical, you only really have to worry about dealing with 1/2 of the molecule for the proton transfer. So I'm going to draw proton transfer. Remember, we're always going to put the proton on the terminal carbon, because that gives us an allylic carbocation intermediate. We also form some bromide in that step. We can draw out the resonance contributors of the allylic carbocation. And then we can show bromide doing a nucleophilic attack at the carbons that share the positive charge. This is going to lead to 2 products. Again, I've left the hydrogen off for simplicity, but the hydrogen would be at this terminal carbon at the very bottom of the structure. So we can label these the 1,2 and the 1,4 adduct. Since the hydrogen was added here, we're going to call this the 1,2 adduct, and this one the 1,4 adduct. But the question asks us to predict which product would predominate at 0 degrees and at 40 degrees. So to know which one predominates at 0 degrees, we need to know which one is the kinetic adduct. So recall that the kinetic adduct is always the 1,2 adduct. So we'll go ahead and label that. And the thermodynamic adduct is whichever alkene is more substituted. This is a tetrasubstituted double bond. This is a trisubstituted double bond. This one is more substituted. This one is the thermodynamic product. The kinetic product predominates at 0 degrees. We'll label this one as the major product at the lower temperature. And we'll label the top as the major product at 40 degrees. Let's go ahead and go back and look at the next question. That states, when the following diene is treated with HBr at elevated temperature, the 1,2 adduct predominates rather than the 1,4 adduct. Explain this result. Go ahead and work on it, pause the video, and then resume when you're ready. Okay, so I began working on this problem before, but basically to recoup what I've done so far, I noticed that this is a symmetrical diene, so I drew in a plane of symmetry. Then I decided that I would first start by drawing both products. So I drew the 1 adduct and the 1,4 adduct. Now I'm going to look at the question again. So the question asks me to figure out why the 1,2 adduct predominates at higher temperature. So normally we know that the 1,2 adduct is the kinetic adduct, right? So it should be major at lower temperature. But which product is the thermodynamic adduct? It is not always the 1,4 adduct. And in fact, it's defined as the most stable product, which is the most substituted alkene. You may notice that the 1,2 adduct is actually a tri-substituted alkene, and the 1,4 adduct is a di-substituted alkene. So this is actually more stable. So this is also the thermodynamic adduct, which explains why it is the major product at higher temperature as well. So we just want to mention, right, that this is a tri-substituted alkene, and this is only a di-substituted alkene. And that explains the stability difference and why the 1,2 adduct is also the thermodynamic adduct. Okay, we're going to move on to a different section now, and we're looking at first an introduction to pericyclic reactions. So pericyclic reactions occur as one-step reactions without any ionic or free radical intermediates, which is very unique for reactions. Usually there's some partial positive or negative charge developing in the transition state if it's a one-step reaction, or charged intermediates if it's a multi-step reaction, for most reactions, which are ionic reactions. Other reactions which have radicals are different, but these reactions don't have any of those properties. There are 3 main types of pericyclic reactions, and we're actually only going to spend time discussing the first type. Although I will introduce the other 2 types, we're not going to go into those in detail. So you can skip those sections in the textbook. The first type is cycloaddition reactions, and those occur when you have a conjugated diene reacting with an alkene to form a cyclohexene ring. One of the hallmarks of this reaction that distinguishes it from the other pericyclic reactions are the fact that we are gaining a net of 2 sigma bonds and losing a net 2 pi bonds in this reaction. The second type are called electrocyclic reactions. They also form a ring, but they start from a 1,3,5 hexadiene structure to generate that ring. In these reactions, we are gaining one sigma bond and losing one pi bond overall, which distinguishes it from cycloaddition reactions. The third type is a sigmatropic rearrangement. In this case, we're starting from a 1,5 hexadiene, and we are getting a different 1,5 hexadiene. Now you may ask yourself, why did you say that's different? Those are the same structure. And that's true in this particular example. However, if you could imagine having a substituent here would end up here, and it would actually generate a different product. So useful sigmatropic rearrangements have substituents that end up migrating to a different position, leading to a new and interesting product. And what distinguishes these reactions from cycloadditions and electrocyclic reactions is that we have no net gain or loss of pi bonds in this particular reaction. All of the pericyclic reactions have four characteristic features. The first is that the reaction mechanism is concerted, and that means it's a one-step mechanism. It proceeds without any intermediates. The mechanism involves a ring of electrons moving in a closed loop, which is very unique, and not a lot of other reactions share that property. The transition state is cyclic. You notice that we were either forming a ring in a couple of cases, or at least having a cyclic transition state leading to another acyclic product. And the fourth is the polarity of the solvent generally has no effect on the reaction rate, which is an indication that the mechanism does not involve any charged intermediates or transition states, because those would be favored with a polar solvent. So the fact that they can get away with using a nonpolar solvent and it doesn't affect the rate shows that polarity in the solvent isn't needed because there's no need to stabilize any charge during the reaction. Here's a table that discusses the difference in the three types of pericyclic reactions in reference to the change in the number of sigma bonds and pi bonds in the reaction. The main reaction that we're going to be talking about for the rest of the chapter is called a Diels-Alder reaction, which is named after two chemists named Otto Diels and Kurt Alder. The Diels-Alder reaction is a Nobel Prize winning reaction in chemistry, and it's a very useful reaction. It's also called a 4+2 cycloaddition because you are reacting a conjugated diene, which has a 4-pi system. You think about the 4 p orbitals involved, and an alkene, which has a 2-pi system, leading to the formation of a cyclohexene ring. If there are substituents involved, those are then attached to the ring. The mechanism is one step, as we mentioned. We call those type of mechanisms concerted. We can draw the arrows, which we need 3 of, going in a clockwise or a counterclockwise fashion. They can be drawn inside of the ring, eventual ring, or outside of the ring, and it doesn't matter. Basically, we have a shift of the pi electrons forming 2 new sigma bonds and shifting one of the pi bonds over. If you look at an energy diagram of the reaction, it's not surprising that it only has one step or one hump, because as we mentioned, it's a concerted reaction. The transition state has partial bonds being broken and formed. You have the 2 new sigma bonds being partially formed, as well as a pi bond between these 2 carbons, and then the pi bonds between the other carbons that are shown here are being partially broken. So it is a cyclic transition state leading to the cyclic product. Most Diels-Alder reactions are thermodynamically favored at low or moderate temperatures, meaning that the reaction is reversible and the forward direction is favored at low or moderate temperature, But the reverse reaction, which we call the retro-Diels-Alder reaction, is actually favored at higher temperature. And that's because when we look at the equation for determining spontaneity, delta G, we're going to see that the entropy and enthalpy play a factor here, and that's why we have a temperature dependence in terms of which direction of the equilibrium is favored at a given temperature. Let's look at that equation. Delta G equals delta H minus T delta S. We can break those two terms apart and call the delta H the enthalpy term, and then take the minus T delta S together and call that the entropy term. So that while there are many factors that contribute to the sign and magnitude of delta H, the dominant factor is generally bond strength. So we're looking at the amount of energy that is broken when we break different bonds and the amount of energy that we get back when we form new bonds. And overall, the process, or delta H, is negative if the amount of energy that's given off exceeds the amount of energy that is consumed when we're breaking certain bonds. So if we look at the overall reaction without doing any calculations, we can make some assumptions here. We know that the bonds broken are 3 pi bonds, and the bonds formed are 1 pi bond and 2 sigma bonds. So overall, this is a net loss of 2 pi bonds and a net gain of 2 sigma bonds. We know that sigma bonds are stronger than pi bonds because they involve head-to-head overlap of atomic orbitals as opposed to side-to-side overlap of atomic orbitals in a pi bond. So because we're forming stronger sigma bonds and breaking weaker pi bonds, we can make a guess, an educated guess, that delta H for most Diels-Alder reactions will likely be a negative and favorable enthalpy term. But what about entropy, right? Will the entropy term be positive or negative? I want to remind you that when the entropy term is favored, its delta S is positive. When it's disfavored, it's negative. So that's a little bit different from delta H. When the enthalpy term is favored, it's negative. And when the enthalpy term is disfavored, it's positive. So the opposite is true for delta S. So delta S for this reaction is actually negative, which means that it's disfavored, because 2 molecules combine to form a single product and a ring is being formed. So what does that mean? Whenever you have 2 reactants combining to form 1, and we have 2 acyclic reactants combining to form a ring, we are losing molecular freedom. And as a result, entropy is disfavored for the reaction. So if we need overall delta G to be negative to have a favorable reaction. So what we want is that the enthalpy term is larger in magnitude and a negative value than the entropy term is in magnitude as a positive value. So in order to have a smaller magnitude of entropy term, it makes sense that that will be favorable or more likely when the temperature is low. When the temperature is low, we're multiplying a smaller number by the negative delta S. Overall, negative times negative will equal a positive term. And if the temperature is lower, hopefully this is an overall smaller in magnitude than the negative delta H, and the reaction will be favorable. So that's why most Diels-Alder reactions will be much more favorable at lower temperature or a gentle heating, and at more extreme temperatures, actually the reverse reaction is favored, because now the magnitude of the entropy term is more likely to be larger than the magnitude of the enthalpy term. So in terms of the Diels-Alder reaction, we have some terminology to be aware of. The reactants are what we call the diene and the dienophile. The diene refers to the conjugated diene, and it's typically the electron-rich component in the reaction. And the dienophile is typically the electron-poor component in the reaction, and only one part of this, or the one alkene, is reacting to form the ring. So typically in most Diels-Alder reactions, the dienophile needs to possess an electron withdrawing group, and that's because the diene is electron rich, so it's more favorable when the dienophile is electron poor, because as we know, things that are electron rich tend to want to react with things that are electron poor, and two things being electron rich are unlikely to lead to a favorable reaction. So for example, we can do a Diels-Alder reaction with 1,3-butadiene and ethylene, but because both of these are electron rich, the reaction is not very favorable, meaning there's a high activation energy and it requires a high temperature for the reaction to go. However, as we know, at high temperature, the retro Diels-Alder reaction is favored in terms of the position of equilibrium, which means that we're going to overall probably isolate a low yield, because again, the reverse direction is favored. So the reaction is much more favorable when one of the components, and usually it's the dienophile, is made electron poor. For example, if we take the dienophile here, which is substituted with an aldehyde, which is an electron withdrawing group, then we can react these two together at a much lower temperature, leading to a fantastic quantitative yield of product. Here's some other examples of different electron withdrawing groups that can be attached to the dienophile to make for a very favorable Diels-Alder reaction. You might note that these are groups withdraw electron density through induction, which means through the sigma bond network, but also through resonance because of the conjugated pi system. So in fact, these dienophiles are actually dienes. They are conjugated dienes, but only the two carbons in black are actually getting incorporated into the ring, and the electron poor component of the diene, which is actually called the dienophile, ends up outside of the ring. Diels-Alder reactions are stereospecific, and depending on whether or not you use a Z or an E alkene, the stereospecificity will translate to the product. So for example, a Z or a cis alkene will end up with a cis disubstituted product, and an E or a trans alkene will end up as a trans disubstituted product. Notice that this product says plus enantiomer and this one doesn't. And that's because this structure has an internal plane of symmetry and is a meso compound and is overall achiral, so it cannot have an enantiomer. Alkynes can also function as the dienophile, and when they do, only one of the pi bonds reacts to form the ring and the other pi bond remains. So the product ends up as a cyclohexadiene. Let's do some practice problems and predict the major products for each of the following Diels-Alder reactions. Go ahead and pause the video and then we'll discuss it when you're ready. Okay, so we are going to start drawing products. And recall that these two carbons are going to function as the dienophile, and then we have our 1,3-diene as the diene component in the reaction. So I'm going to start by drawing the cyclohexene ring that's part of the product. And then noting that these are trans cyano groups, I'm going to end up drawing them one back and one forward, maintaining that trans relationship. This is not a meso compound, so I also need to write plus enantiomer. Looking at the second one, we have another cyclohexene ring being formed. And we have two methyl ketones attached, and their relative orientation is cis or Z. They will both end up or both end up down. And it doesn't matter which one you draw because the product is going to end up as a meso compound. So those two structures are actually identical. In this case, we're looking at an alkyne acting as the dienophile. It can still react, but we will get a 1,4-cyclohexadiene. There is one carboxylic acid. We don't need to worry about stereochemistry because this carbon remains sp2 and trigonal planar. In this case, we're forming a ring, but it's actually going to be attached to another ring. So we're forming now a 6,5 system. We can draw in fused bicyclic system. We'll end up with a cyclohexene here. Notice that because of the ring, these are essentially in a Z or a cis format. So these groups will both end up or both end up down. It doesn't matter because it's a meso compound. Let's do another practice problem. Identify the reactants that you would use to prepare each of the following compounds via a Diels-Alder reaction. So if you want, you can sort of work backwards. Think about doing the retro Diels-Alder reaction to get back to the reactants. Go ahead and pause and then resume when you're ready. Okay, let's go ahead and start working on it. One thing we could do, it didn't ask us to do it, but we could draw in reaction arrows to go back to the reactant. So sort of drawing in the mechanism for the retro Diels-Alder reaction. So what we can do is we're going to break these sigma bonds, and we can kind of go clockwise or counterclockwise with the rotation, and it wouldn't matter. I'm going to choose to go counterclockwise here, and that's going to lead me to the two reactants, which are our butadiene. And also notice the relative stereochemistry. These are both up. So this should have been a cis disubstituted dienophile. Doing the same analysis with the other one, we're going to draw the same arrows. Looking at the retro Diels-Alder reaction. In this case, we have a methyl group here. So the diene is going to possess that same methyl group. And then the trans disubstitution means that the two groups were trans, or E, in their relative orientation before the reaction. Let's talk a little bit more about the diene. Recall that dienes can exist in an S-cis or S-trans conformation, and they can interconvert via rotation of the single bond that's in between the two pi bonds. You might have noticed that we've been drawing the diene in an S-cis conformation in all of the previous examples. And that's because the diene must be in an S-cis conformation in order to react in the Diels-Alder reaction. And that's because both terminal carbons are involved in making the new sigma bonds that complete the new cyclohexene ring. So in order for those two sigma bonds to form simultaneously with two alkene carbons, they need to be close to one another in that S-cis conformation. So dienes that are trapped essentially in an S-trans conformation cannot undergo the Diels-Alder reaction. And the reason why it's trapped is because this single bond cannot rotate. It cannot rotate because of the ring constraining that rotation. If we were to rotate the single bond, the ring would have to break to allow that to happen, which is not going to happen. So even though this is a conjugated diene, it actually cannot undergo a Diels-Alder reaction because it's not able to get to an S-cis conformation. In contrast to that, dienes that are locked into an S-cis conformation because they're part of a ring, they react extremely rapidly in Diels-Alder reactions. For example, cyclopentadiene will react very quickly with this dienophile, leading to a bicyclic product. You might be wondering, how can I draw or think about this bicyclic product? Well, the carbons from the diene are shown in red. You can see that as these two new sigma bonds come together, we just push the bridge between the two carbons that end up forming the sigma bonds up and end up placing the alkene sort of in the plane. The halogen groups, which are just designated with a generic X, they are trans. They have a trans relationship in this alkene, so they'll end up with a trans relationship in the bicyclic product. Notice that with bicyclic products, we don't draw dashes or wedges. We just draw the groups as either sort of pointing up or pointing down. Right here, this one's kind of pointing up and pointing down. You can think of it as sort of similar to when you draw a chair structure, having sort of an axial versus equatorial position there. Cyclopentadiene is so reactive towards Diels-Alder reactions that it would actually react with itself at room temperature in a matter of 1 or 2 hours. So if cyclopentadiene is left out at room temperature, it actually undergoes a Diels-Alder reaction with another cyclopentadiene. In one case, we have one molecule acting as the diene, and the other molecule, only one of the pi bonds reacting as the dienophile. This leads to a compound that is bicyclic, and we call it dicyclopentadiene. And it also, it's formed as a racemic mixture or a mixture of enantiomers. And the way but remember that Diels-Alder reactions are reversible, right? So while we see the arrow going this way, we can also go back. Recall that to go back, all we need to do is heat the Diels-Alder product to a high temperature. So if we actually heat dicyclopentadiene to 200 degrees or more, it will go back to cyclopentadiene, and we call this procedure cracking. So anybody who wants to use cyclopentadiene actually takes if the sample previously had been stored at room temperature, they have to first crack it and then use it immediately or store it in a refrigerator until they're ready to use it. So we talked about the fact that the diene has to exist in an S-cis conformation in order to react. So let's practice rotating from from S-trans to S-cis, because you'll recall that the S-trans conformation is actually more stable. So it's common to see conjugated dienes drawn in the S-trans conformation because it's the most stable conformation. However, we know we can do a rotation about the single bond in order to rotate into an S-cis conformation. And then we can potentially do a Diels-Alder reaction from that positioning. So let's go ahead and practice and learn some tips for doing that and making sure not to make any mistakes in the process. Okay, so recall that we are going to be rotating, right, this central single bond in between the two pi bonds. So what I like to do is actually pick half of it to keep it the same. And so draw that single bond. I'm going to say the top half doesn't move. I'm sort of drawing this same. And then take the bottom half and flip it over like a pancake, right? So we're going to flip this over 180 degrees, and we'll end up with it pointing this direction, right? And then the methyl pointing down. So sometimes students will want to put this methyl group pointing in. how do we know not to do that? Well, one strategy that you can use to double check is to think about if the alkenes here can be labeled E or Z or cis or trans. So for example, this particular alkene that I didn't move has two methyl groups. Those are identical groups, and they're on opposite sides of the pi bond. So I could call this alkene trans. However, the methyl group and this other group take priority, right? So when I'm looking at priority groups, this group is going to have priority over the methyl, and this methyl has priority over the hydrogen. So my two priority groups tell me that this is actually a Z alkene. So I could label this trans or Z. If I'm looking at this particular alkene, and I have hydrogens that are opposite one another, so this one could also be called trans. Those are identical groups, hydrogens. But my priority groups are, this group has priority over the hydrogen, the methyl has priority over this hydrogen. So the priority groups are actually opposite each other. So both are actually considered trans, but one is Z and one is E. And you can look back at the review video that was released in the first week to see that in more detail if you're having trouble deciding if it's cis or trans or E or Z. Okay, so one of the things I wanted to mention is that that should not change after rotation. If all we're doing is rotating about a single bond, then I'm not changing E to Z, right, or vice versa, and I'm not changing cis to trans and vice versa. Because recall, we cannot rotate these double bonds, right? We're only rotating the single bond. So as we come over here and look at this, this should still be trans and Z, and this should still be trans E. And it is, so I know I did not make any mistakes. If I was to have placed this methyl in here, I now would have gotten a cis or Z double bond, and I know I would have made a mistake. And then the last thing that you can do is if you want to, you can sort of rotate it a little bit to look like we've been seeing the dienes look so far. So recall that when we're reacting with a dienophile, it's called something with an electron withdrawing group, right? This is our dienophile, this is our diene. Usually we align them sort of with the diene looking like this and the dienophile looking like that. So this is just kind of a little rotation in the plane to get it to be able to align with the dienophile. Okay, I wanted to show you a picture of a handout that I'm linking on Canvas for you guys to print out and use if you would like. And that takes you through a stepwise process for predicting the products of a Diels-Alder reaction. And what we've been talking about so far is actually step one, which is getting the diene into the correct S-cis conformation. If you're given the diene in an S-trans conformation, the first step you need to do is rotate the single bond to get it into an S-cis conformation. If you're given the diene already in an S-cis conformation, then you don't need to do that rotation. You can move directly to step two, which is about regioselectivity, which we'll talk about in a minute. First, let's do a practice problem. In each of the following cases, rank the compound in terms of increasing reactivity as dienes in a Diels-Alder reaction and explain your ranking. You'll need to do some S-trans to S-cis interconversions to answer part A, and but probably not to answer part B, although you could rotate this one if you'd like. Go ahead and pause the video, work on it, and then resume when you're ready. Okay, let's go ahead and go over this. So we want to maybe in terms of increasing reactivity in the Diels-Alder reaction as a diene. Both of these right now are given to us in a S-trans conformation, and figuring out the difference, well, actually, it'll be easy for us to see that once we're writing this into an S-cis conformation. So what we can do is, like I told you before, keep one half steady, right, or don't move one half, and then just flip the other half over like a pancake. So for example, I could keep this part on the bottom looking the same, and then just flip this one over. You can sort of just kind of flip that over so it looks like that. Now it is in an S-cis conformation. And even though S-trans is more stable, we do need it to go into S-cis in order to react. Let's do the same thing for the other conjugated diene. We need to go ahead and flip that over. So again, we want to take one half and hold it steady, and then flip the other half over. So if you want, you can sort of draw it, the single bond that you're going to be rotating in, and then keep one half of it looking the exact same, right? And then take the other half and essentially flip it right over. We'll end up with that. And again, you can, this is a cis double bond, this is a cis double bond. It should end up as a cis double bond and a cis double bond, or a Z and a Z alkene. So either way. So now when you see this, it might be a little bit more clear what you think will react faster. So in terms of the stability here, of course, S-trans is always more stable. Let's look at this S-cis conformation and compare it to this S-cis conformation. We have a little bit of a steric hindrance problem here. The problem is that there are methyl groups and they're both pointed in. So those are definitely going to run into steric hindrance in an S-cis conformation. The steric hindrance is going to make this particular S-cis conformation a lot less stable than this one, which is going to lead to an even greater equilibrium favoring the S-trans conformation. So in a way, it's like we have a situation where something rarely goes into the S-cis conformation, or the concentration of this is very low because this is very unstable. Whereas even though we favor the S-trans conformation, in this case, there's no steric hindrance, so there'll be a greater percentage of molecules in the S-cis conformation. Since this exists a little bit more often in the S-cis conformation, it's going to make for a faster Diels-Alder reaction. Right? So this one is going to be, in terms of increasing reactivity, we'll say this has the lowest or the slowest reactivity and the highest or the fastest reactivity. Okay, looking at part B, you might have noticed that this particular conjugated diene is locked in an S-trans conformation. That means that it cannot undergo a Diels-Alder reaction. So by definition, that one is definitely going to have the lowest reactivity because it has no reactivity, right? In a Diels-Alder reaction. So, you know, we're ranking it as lowest, but it really has no reactivity. In contrast to that, this structure is actually locked in an S-cis conformation. And that means that it's always in an S-cis conformation, so it's going to react very quickly. In comparison to that, this one is not locked in an S-cis conformation. So even without rotating this into an S-cis conformation, I can already tell this one is definitely going to have the highest reactivity because it's always in an S-cis conformation. But if we do want to just practice, right, rotating the S-trans conformation into an S-cis conformation, we can do that. And we can draw the cis conformation by just keeping one half of this molecule the same, right? And then flipping the other one over. So we're going to take this and essentially flip it over. And when we do that, the diene is going to point in. There'll be a methyl group here, and then there'll be a methyl group pointed out there as well. And this doesn't have any horrible steric hindrance, but still the molecule will not exist in this conformation all the time, so this is expected to be slower. Okay, let's talk about bicyclic systems a little bit more. Recall that when we have a cyclic diene, so in this case cyclopentadiene, and it's reacting with a dienophile, it forms a bicyclic ring. Well, there are two potential products that can be formed here starting from this cis dienophile with two of these aldehyde groups. Note that because these are on the same side of the double bond, they will end up on the same side in the product. But we can still get more than one product depending on the relative orientation of the two aldehyde groups as the dienophile is approaching the diene. And we can end up drawing what we call an endo product and an exo product. So where do these terms endo and exo come from? They actually come from their relative proximity to the other bridges in this bicyclic structure. So notice that there are three bridges. There are the one coming from the dienophile, and then there's the larger bridge coming from the diene and the smaller bridge coming from the diene. So we're going to be talking about the positioning of the groups with respect to the larger bridge in the bicyclic structure, which it also forms the alkene. So when it's syn to the larger bridge, we call this the endo position. And when it's sort of opposite or anti to the larger bridge, we're going to call this position exo. So then it's a question of what is preferred, right? Will the aldehydes end up exo in terms of a major product, or will they end up endo in terms of a major product? You might expect that whatever one is more stable would be the major product, but this is actually not the case. The endo product is actually the major product, even though it's not as thermodynamically stable as the exo product. The reason why it's not as thermodynamically stable is, again, the bulky groups are closer or syn to the larger bridge, which is more has more steric hindrance. So when they're exo, right, or away from the larger bridge, then they're closer to the smaller bridge, which is a little bit more stable. So what is the explanation for why we get the endo product as the major product? And I told you it has to do with relative positioning or of the electron withdrawing groups, the aldehyde groups, as they approach the diene in the Diels-Alder reaction. So note that the diene and the dienophile are largely trigonal planar because all the carbon atoms here that you can see are sp2 hybridized. And the geometry is trigonal planar as a result. So when the molecules are reacting, it's actually sort of a top to bottom sort of orientation. And typically we view the dienophile approaching from the bottom, but that's just by convention because it's a little bit easier to draw that way. The dienophile also approaches from the top and would lead to an enantiomer if one exists. So the reason why the aldehyde groups prefer to be sort of endo with respect to what becomes the larger bridge, sort of are pointing in with respect to the diene, I like to think of it, is because there is a developing favorable interaction between the pi bond on these two carbons and the pi bond of the carbonyl. Specifically, the p orbital on this particular carbonyl carbon can overlap with the p orbital on one of these interior carbons. And that actually happens on both sides in this particular example. And that interaction, although it doesn't lead to a new bond, it temporarily stabilizes the transition state, leading to a lower energy pathway. And the Diels-Alder reaction is kinetically controlled. And so the faster forming product is trapped as the major product. So you can see that now we're starting to form signal bonds. And then as we rotate this so that it looks like this six-membered ring, the aldehydes end up pointed down. We call that endo because of the positioning with respect to the diene. The other possible orientation is the aldehydes are pointed out when the dienophile approaches the diene. This would be too far for any favorable interaction between the p orbitals of the carbonyl and the p orbitals of the interior carbons on the diene. So there's no favorable interaction, and it's going to lead to a slightly higher transition state energy, and this is just not going to form as quickly, so it won't lead to the major product. So again, the endo transition state is lower in energy, right? Even though it doesn't form the most stable product, it is the major product because the Diels-Alder reaction is kinetically controlled at lower temperature. Let's do a practice problem to practice drawing these bicyclic structures. Recall that when we draw bicyclic structures, we don't need to draw any dashes or wedges to indicate stereochemistry. We just need to draw the substituents either sort of pointed down and, quote, sort of axial-like or sort of out and equatorial-like. But basically, you can think of it as truly the endo or exo positions. Go ahead and pause the video, and then we'll talk about it when you're ready. Okay, let's go ahead and go over how to do these problems. So the first part is practicing drawing these bicyclic structures. So I have a cyclopentadiene, and the way I'm going to draw it is with the pi bond. And then I'm going to sort of come up here for the two and put this methylene up, right? So it ends up looking like this after the Diels-Alder reaction occurs. Right? You can even draw in the new sigma bonds that get formed in a different color just to really highlight those. And this is going to be the rest of that six-membered ring. Now notice that we have two substituents. They are a cis positioning on the alkene, so they're going to end up in a cis positioning on the product. And because they'll prefer an endo position, they will both end up down. So we're going to draw those, as opposed to drawing them out, we're going to draw them down. Notice that there is an internal plane of symmetry. We can just slice that right in half. And so we don't need to write plus enantiomer because this is a mesopolymer. Let's move on to the next structure. This is a very similar reaction. We're just starting off with a trans day substituted dienophile. We're drawing in the product. We can do it the same way. We just need to get the relative positioning of the substituents correctly. Now, only one of these can be faced endo at a time because of the transpositioning, which means one will be endo and one will be exo. So I just need to make sure to draw one down and the other one not down, instead out like that. And you can even draw in the hydrogens here to show where they end up. So you can see that one ends up sort of in the exo, and one ends up pointed down in the endo position. This one does not have a plane of symmetry, and so does have an enantiomer. We want to make sure to write plus. All right, let's go ahead and practice drawing the bicyclic product that might result in this case. This one we haven't seen before, but it's still a cyclic diene, but it's a 6-membered ring instead of a 5-membered ring. There's no problem there. We can kind of start off drawing it the same way, but instead of drawing a 1-carbon bridge up here, we're going to end up drawing a 2-carbon bridge, like that. And then we can draw in new bonds that form to the dienophile. And we can start to connect those two. And then we can see here that there's cis positioning and it's part of a ring. So we actually do need to draw them pointed down because these groups will prefer an endo orientation. But we need to be careful and draw it as part of a ring. So this is actually a little bit of a challenge to draw this, right? But we can do our best. Sort of attempt to connect those fast, and then we have the exo positions occupied by hydrogens. This does have an internal plane of symmetry, so no need to draw plus and minus. Looking at the next example, we just have an oxygen as part of the ring, no problem at all. It's exactly like a 5-membered ring. We're just going to connect it to an oxygen. Then we can start connecting this to the dienophile. Notice that we only have one substituent as a methyl ketone, but it's going to prefer an endo position, so it's going to end up down. So we can either put it down on this carbon or down on that one, and it won't matter. It's easier to draw it on this one, so I'm going to go ahead and do that. This one does not have a plane of symmetry, so it does have an enantiomer. Right, plus 10. Okay, the next topic we want to talk about is the regioselectivity in the Diels-Alder reaction. So when you're looking at a Diels-Alder reaction, remember the first step is to get the diene in an S-cis conformation. Once you're done with that, you can move on to looking at regioselectivity. The first step when you're looking at regioselectivity is to determine if either the diene or the dienophile, or maybe even both, have an internal plane of symmetry. If at least one of those, either the diene or the dienophile, have an internal plane of symmetry, then we don't have to worry about regioselectivity. We can just combine the two components to form the ring and then move on to stereoselectivity after that. So these are examples where there's no issue of regioselectivity because essentially only one possible constitutional isomer can form due to the symmetry here. Let's look at an example where both the diene and the dienophile do not possess an internal plane of symmetry. It's in these cases when we really need to worry about regioselectivity because as we can see, it's possible for the dienophile to approach the diene in two ways. In this direction would lead to the minor product, but if we actually flip this over and have it approach the diene, it will end up with another product entirely, which is actually the major product. The major and minor product are related as constitutional isomers. So this is an issue of regioselectivity, where one is formed as the major product or greater than 50% amount, and one is formed as the minor product or less than 50% amount. So how can we predict then which will be the major product and which will be the minor product? That is the question. So to predict it, what we need to do is draw out resonance contributors of both the diene and the dienophile to look at where the partial charges are located. When we draw the resonance contributor of the diene, we can draw an allylic lone pair pattern, which shows that we have a partial negative charge on this terminal carbon that's part of the diene. There is no resonance contributor which will place a partial negative charge on the bottom carbon. That's of importance to note. When we're looking at the resonance contributors of the dienophile, the first pattern is pi bond between atoms of different electronegativity. We can move the electrons in the pi bond to a lone pair on the more electronegative atom, which in this case is an oxygen atom. That will leave the oxygen atom negatively charged and the carbon atom positively charged. We can keep going with resonance in this case because we've now uncovered an allylic carbocation. We can do the allylic carbocation pattern to shift the pi bond to between these two carbons, which also shifts the carbocation to this carbon. So this is the most important resonance contributor because the positive charge is on this carbon, and this is one of the two carbons that are involved in forming the new sigma bonds in the Diels-Alder reaction. And I only really care about partial positive charges on the terminal carbons of the diene, because again, those are the carbons involved in forming the two new sigma bonds with the dienophile in the Diels-Alder reaction. So we need to locate the partial charges specifically on the carbons involved in forming the new sigma bonds and align them so that the attractive forces that result from opposite charges are allowing for an electrostatic attraction, which leads to a lower energy transition state in the Diels-Alder reaction. So what we actually needed to do is flip this entire dienophile over so that there's an alignment between the delta negative carbon on the diene and the delta positive carbon on the dienophile. And this electrostatic attraction, again, results in a lower energy transition state. And it's all about the transition state because the Diels-Alder reaction is kinetically controlled. So we end up giving this as the major regioisomer, aka constitutional isomer, as the product. Regioselectivity is step 2 on the handout that I provided to you on Canvas. So once your diene is in an S-cis conformation, you need to analyze for the presence of internal planes of symmetry on either the diene or the dienophile. If one exists, then we don't need to worry about regioselectivity because it won't be an issue and only one possible regioisomer is possible. If there is no plane of symmetry on either the diene or dienophile, then we need to locate partial charges to align them in order to predict the major regioisomer. In either case, we are then going to move on to step 3, which is stereoselectivity. Before we do that, let's do a practice problem dealing with regioselectivity. The goal here is to predict the regiochemical outcome, or the major product, for each of the following Diels-Alder reactions. For now, we're going to ignore stereochemistry, so don't worry about placing groups on chiral carbons on a dash or a wedge. Just leave them as a regular bond, and we'll worry about stereochemistry in the next step. But the goal here is look for planes of symmetry in either the diene or dienophile, determine if we need to worry about regioselectivity. If we do, we need to figure out where the partial positive and negatives are and make sure to align the opposite charges to predict the correct regioisomeric product. Go ahead and pause it, do your best, and then when you're ready, we'll discuss. Okay, let's go ahead and start predicting the product. So right here, I can see that there is no internal plane of symmetry on the diene. There is also no internal plane of symmetry on the dienophile. As a result, we are going to need to concern ourselves with regioselectivity. So what you can do is draw out the resonance contributors of the diene and the dienophile. I'm just going to do a shorthand version of that. And I'm going to start with the lone pair on the oxygen and push electrons all the way to this terminal carbon. Notice that I will never be able to get a delta negative on this carbon because the delta negative ends up here and here, right? And I don't really care about a delta negative on that carbon because it's not one of the carbons that is going to be aligning with the dienophile to make the new sigma bond. So as a result, I can label this carbon as my delta negative. When I do resonance contributors of the dienophile, I'll do pi bond of differing electronegativity, and then I'll do a Lillich positive charge, and I'll end up with a delta positive on this top carbon. Right now, these are not properly aligned. You can see that the delta negative and delta positive, right, are not aligned properly. So this is, right, this is incorrectly aligned. So the correct alignment then, we can draw, we don't have a lot of room, but we'll try to draw it down here. Basically just flip either the diene or the dienophile over. By custom, we usually flip the dienophile over, but it doesn't really matter. We flip this over so that we get the proper alignment. Again, I can make sure that my delta negative and my delta positive are now properly aligned. This will lead to the major regioisomer. So I can draw the product here. I like to sketch in the cyclohexene ring first, and then I'm going to place the methoxy group up here and the methyl ketone on the adjacent carbon. And again, even though these two carbons are stereocenters, we're going to ignore stereochemistry for now. Let's look at the next case. In the next case, we're given the diene in an S-trans conformation. That's a problem. I need it to be in the S-cis conformation in order to react. So what I can do is redraw this, where I'm essentially going to flip over one half of the molecule. And I'm also going to kind of rotate it so I can align it nicely with the dienophile. And then my dimethylamino group ends up on one of the interior carbons. So once I'm in a S-cis conformation, then I can worry about proper alignment. What we're going to do is look at resonance. And resonance will show us that the delta negative ends up on this carbon with respect to the diene, because we start pushing electrons on the nitrogen in the allylic lone pair pattern. And then in terms of the dienophile, let's draw out the nitro group to see what those resonance contributors would actually look like. So we can actually draw the nitro group out. There's a positive charge on the nitrogen and a negative charge on one of the oxygens. And then when I'm drawing out resonance, what I can do is move this is pi bond between atoms of differing electronegativity. Remember, oxygen is more electronegative, so I'm going to give the electrons to the more electronegative atom. That will result in a 2 positive charge on nitrogen, which is unreasonable, so I'm not even going to draw that. At the same time, though, I can shift the pi bond down to relieve one of those positive charges. And that will allow me to visualize a delta positive actually at this top carbon. So it looks like these are already going to be aligned and I don't need to flip the dienophile over. I'm just going to copy it exactly like it was, draw in the delta positive, and then note that those are properly aligned and draw the product. And sketch in the cyclohexene ring. Place the dimethylamino group here. Note that this has not become a stereocenter. So even if we were worried about stereochemistry, we wouldn't draw it as a Thatcher wedge because it's not a stereocenter. The nitro group, however, does end up as a stereocenter. However, we are going to ignore that information for now. Okay, moving on to C. Now we're going to be forming a bicyclic ring, but note that I do not have a plane of symmetry on either the diene or the dienophile, so I do have to worry about regioselectivity. If I'm thinking about resonance contributors, I am going to start from the lone pair on the oxygen and push electrons, and eventually I'll end up with a lone pair on this top carbon, so I'm going to label that my delta negative. If you're thinking about how to draw the resonance contributors with a nitrile, nitriles are carbon-nitrogen triple bonds. We can do resonance the same way. This is a pi bond between atoms of differing electronegativity. So I can give the electrons to the more electronegative nitrogen atom. And then at the same time, instead of worrying about the positive charge that results here, I can shift the pi electrons over to do the allelic positive charge pattern. That's going to lead to a delta positive at this bottom carbon, which means my delta positive is here, and the way it's currently drawn is incorrectly aligned. Right? So I'm going to need to flip one of these over. So I can redraw this to show the proper alignment. Now we do have the delta negative aligning with the delta positive, and we'll get the correct regioisomer. Because this is going to be forming a bicyclic ring, I'm going to go ahead and draw like we were practicing before, with the bridgehead coming up here. And we will also have the bonds, the new sigma bonds to the dienophile. Remember that the cyano group will preferentially occupy an endo position, and it will end up being down. That is not ignoring stereochemistry, but since we already went over it, it's okay to go ahead and place that in. And then we also have a methoxy group, an ethoxy group here as well. This is not a meso compound, so it has an enantiomer, so we should get plus an enantiomer. Looking at the last example here, I'm looking for an internal plane of symmetry on either the diene or the dienophile. And I note that I do actually find one in the dienophile, which means I don't have to worry about regioselectivity, and the way it's currently shown is fine for alignment because there's only one possibility. So I'm going to draw in my cyclohexene ring, add in the methoxy group, and then add in the dienophile, which is also a ring, so we'll get a fused bicyclic product. I do end up with two stereocenters here, but again, I'm not going to worry about it at this time because the instructions told me I could ignore it. Okay, the only one that really included stereochemistry is this one, and that's because we had already talked about the endo and exo positioning in a previous example. The rest of it we will need to learn a little bit more about before we can include that information when we're predicting the product. But before we do that, let's talk a little bit about molecular orbital theory again, with respect to why it's important for cycloaddition reactions. Let's consider the simplest 1,3-diene and dienophile, which would be 1,3-butadiene and ethylene. So with 1,3-butadiene, recall we have 4 overlapping p orbitals forming 4 molecular orbitals. We have the HOMO and the LUMO labeled, And then for a simple alkene, we would just have these two molecular orbitals, and then the bottom bonding molecular orbitals, of course, the HOMO, and the top one is the LUMO. So remember that I said that the frontier molecular orbitals are the ones that are important. And the frontier molecular orbitals are the HOMO and the LUMO, because those are going to be the ones involved in the reaction. So how do I know if I'm utilizing the HOMO of the diene and the LUMO of the dienophile, or the opposite, the HOMO of the dienophile and the LUMO of the diene? And the answer is it depends on which component is electron rich and which component is electron poor. Typically, the diene is the electron rich component and the dienophile is the electron poor component. In that case, the electron-rich component is kind of like the nucleophile, and the nucleophile, as we know, donates to the electrophile, which is the electron-poor component. If the nucleophile is going to donate electrons in its pi system, where are they going to come from? They're going to come from the HOMO, because the lower energy electrons are kind of like the core electrons. They're more stable, so they're unlikely to want to be donated to another molecule. So we're going to donate electrons from the highest energy electrons that we have, which are the electrons in the HOMO, and we're going to donate them into the dienophile's LUMO, because again, it's the electron poor component, so it's acting as the electrophile. It will receive electrons from the nucleophile. Where can it receive them? Well, it can't receive them in its HOMO because it's already filled with electrons. But it could receive them in its LUMO because that is currently unoccupied by electrons. And then, so initially the HOMO will donate into the LUMO, but then as bonds break, these will rearrange and we'll get a relaxing of electrons down into more stable orbitals. Again, the HOMO of one interacts with the LUMO of the other. The one that's electron rich will use its HOMO to donate to the one that's electron poor, which will use its LUMO to accept those electrons. So essentially, the orbitals that are important are only the HOMO of butadiene and the LUMO of ethylene. So what this is a picture of those drawn in with the alignment as the dienophile approaches the diene from the bottom. So we've redrawn the HOMO of butadiene, which has a node here, right? Which means that we're going to flip the sign. There's going to be no orbital overlap. And then we're also using the LUMO of ethylene, which if you look back on the previous slide, there's a node here. So of course the sign should change. So as we draw the HOMO of the diene and the LUMO of the dienophile and attempt to align them as the Diels-Alder reaction takes place, what we notice is that there is conservation of orbital symmetry, which basically means that on both sides there's constructive overlap. And that means constructive overlap can lead to a bond. And of course, in the Diels-Alder reaction, we're simultaneously forming two new sigma bonds. Right now, these are p orbitals, but as they start to overlap, they change their hybridization into sp3 hybridized orbitals, which means the red lobe will elongate and the blue lobe will get smaller as the p orbital morphs into an sp3 hybridized orbital. The same thing is happening with this p orbital. It is changing into an sp3 hybridized orbital, and then that head-to-head overlap is going to be the formation of this new sigma bond. The same thing is happening on the other side with these two blue lobed orbitals. The p orbitals are morphing into sp3 hybridized orbitals as that bond is forming, and the electrons are occupying the space to form a new sigma bond. So notice that this is happening because all four of these carbons are changing from sp2 to sp3. sp2 hybridized carbons have an unhybridized p orbital, but sp3 hybridized carbons do not. They have 4 hybridized orbitals, all of which are sp3. So there is no p orbital anymore. Those have changed to hybridized orbitals, specifically sp3 hybridized orbitals. Okay, so I'm going to expand a little bit in this section on the stereoselectivity of the Diels-Alder reaction. I want to make a note that this expansion is not included in the Klein textbook. So as you're looking at the slides labeled Diels-Alder stereoselectivity 16.x, just note that you're not going to find this information in the Klein textbook, although you can look on the internet for other resources. So again, we're going to be revisiting and expanding on the stereoselectivity of the Diels-Alder reaction. Here I've drawn in a diene and a dienophile and just randomly labeled all the different substituents that are possible on the diene and dienophile. So the diene can have attached to its 4 sp2 hybridized carbons, can have up to 6 groups attached. And then the dienophile can have up to 4 groups attached to the 2 alkene carbons, leading to potentially up to 10 groups attached to the cyclohexane product. But the important part here is the rehybridization. Notice that 4 of these carbons rehybridize from sp2 to sp3. So we form 4 new, potentially new chiral centers. They're only chiral centers if they have 4 different groups attached, but you have the potential to form up to 4 new chiral centers because we're forming 4 new sp3 hybridized carbons. So the book, when they talked about stereoselectivity of the Diels-Alder reaction, they only really told you about relative stereochemistry of groups on the dienophile and their placement in the product. But what about the blue carbons, right? Those also become sp3 hybridized. They have the potential to become chiral centers. How would we draw in and figure out the chirality of those 2 carbons if there were substituents attached? That's what we're going to be talking about here. So as the dienophile approaches the diene from below, and again, that's just by convention, we show the dienophile approaching from the bottom face of the diene. It has the equal probability of approaching the diene from the top. And when that's the case, everything happens in the exact opposite way. Rotations occur in the exact opposite way, and we lead to an enantiomer if one exists, or the same product if it happens to be a meso product. So what I did here is just look at the substituents at these terminal carbons and also the substituents on the dienophile. Again, it's because those carbons are the ones that are turning into sp3 hybridized carbons, which are potentially going to become chiral centers. What happens when we have the overlap of the p orbitals here during this alignment as the molecules approach one another is we end up with the pi bond shifting. So recall that these bonds are becoming single bonds. These 2 carbons are becoming a double bond in the reaction. We're forming these 2 new sigma bonds. This pi bond is becoming a single bond. Because these carbon-carbon bonds that I'm looking at right now and highlighting with the cursor, because they are becoming single bonds, they start having access to free rotation. Recall that we can rotate single bonds, but not double bonds. And they actually rotate in opposite directions. This single bond rotates in a clockwise direction, and this one rotates in a counterclockwise direction. And it does so because of the bottom lobe of the p orbital overlapping with the dienophile's p orbitals and eventually leading to these new sigma bonds, which point in opposite directions. So the bottom lobe needs to rotate one direction to form this bond, and the bottom lobe on this carbon needs to rotate opposite direction to form a sigma bond going in the opposite direction as this one. So it's because of the fact that it's forming a 6-membered ring. So when this carbon-carbon bond rotates in a clockwise direction, the group that's pointed in here ends up, and the group that's pointed down ends up down, right? So Y ends up rotating up when this bond is rotated clockwise, and Z ends up pointed down. And the exact opposite occurs with this carbon. Because we're doing a counterclockwise rotation, then X ends up and W ends up down. What you can do is remember that the groups that are pointed in both rotate up, and the groups that are pointed out both rotate down. So notice how I have X and Y here rotating up, and they become the groups that are on a wedge. W and Z end up down, and so those end up becoming the groups on a dash. What about the dienophile? Right? How is that rotating? Well, first of all, we need to understand where's the electron withdrawing group. Of course, the electron withdrawing group prefers an endo position, and that will lead to it being in either position A or B. So as it approaches from the bottom, the entire dienophile rotates a counterclockwise direction, and A and B, which were the endo positions, end up down. C and D, which are the exo positions, end up up. So I know that's a lot of information, so we're going to go through that again a little bit more slowly with a specific example. But I just wanted to show you the handout again, just to show you that stereoselectivity is the third step, right? And when we're generating chiral centers, we need to know if we should place those groups on a dash or a wedge. So this can be a little cheat sheet for you while you're learning to figure out where to put these groups. But eventually, of course, when you're taking the exam or quiz, you won't be able to use the handout. It's just there for your learning process. Okay, so as I mentioned, we're going to be looking at a specific example because I think when we're trying to figure out chirality, it really helps to see a specific example and not a bunch of A, B, C, D, X, Y, Z, etc. So for me, at least, it really helps to visualize it with a specific example. So we're going to be looking at predicting the products of a Diels-Alder reaction between this diene and this dienophile. And the goal is to be able to draw the product with the entirely, right, considering all three steps. So rotating the S-cis, considering regioselectivity, and also considering stereoselectivity. So the first thing we need to do is look at the handout and think about step one. Right now, our diene is given to us in an S-trans conformation. So the first step is needed. We need to rotate this into an S-cis conformation. So what I've done here is just held the top part of this steady and flipped the bottom half over. Right? So we flip it over and now it's in an S-cis conformation. So that is the first step, right? And then we can move on to step two once we get the diene in S-cis conformation. Next, we need to consider the relative orientation of the molecules when they approach one another. This will lead to the regioselectivity. So for example, will the dienophile approach this orientation, which we're going to call approach A, or in this orientation, which we're going to call approach B? And note that I looked for an internal plane of symmetry on the diene and the dienophile first and didn't find one, which is why I need to consider these different approaches, right? And the alignment is correct in approach B, but not in approach A, because the delta negative here is aligned perfectly with the delta positive in the formation of this new sigma bond. So this will be the major product. But again, how did I know where the delta positives and delta negatives are? In order to know where those are, you need to draw out resonance contributors. For the diene, we always draw out the allylic lone pair pattern to figure out where the delta negative is. For the dienophile, typically it's the pi bond between atoms of different electronegativity, followed by the allylic carbocation pattern, in order to figure out where the delta positive is on the dienophile. And then it's just about aligning those properly so that we get the attraction of the opposite charges leading to a lower energy transition state. So once those are aligned properly, I'll be able to show the correct constitutional isomer that's formed. How many chiral centers are formed here? We actually formed 3 new chiral centers. So we need to understand, should I be placing these groups on a dash or a wedge? Right? And that's what we're going to be talking about here. With 3 new chiral centers, there are technically 8 possible stereoisomers if you use the formula 2 to the n, where n is the number of stereocenters. So 2 to the 3 equals 8, so there are 8 possible stereoisomers. However, the Diels-Alder reaction is highly stereoselective, and only 2 of those 8 possible stereoisomers, and they happen to be related as enantiomers, are actually produced in this reaction. So now it's going to be our job to figure out which 2 stereoisomers related as enantiomers are actually formed. So to predict the configuration at each of those 3 new stereocenters in the product, you need to analyze the transition state leading to the product. So again, let's imagine the dienophile approaching the diene from the bottom. And I've drawn in the relevant p orbitals from the HOMO and the LUMO that are necessary to show the reaction. So the overlap that I'm showing you in red here, right, that is the overlap that forms the 2 new sigma bonds. So we're going to call that the primary orbital overlap. There's also the overlap that occurs between the p orbital on the electron withdrawing group and one of the interior p orbitals on the diene. This is also in phase. Notice that the same colored lobe is overlapping on both of these. So this is a favorable interaction, but because it doesn't lead to a new bond, we're just going to call this secondary orbital overlap. With the exo approach, this p orbital is too far apart from this p orbital, and there's no favorable pi interaction. So the exo approach is a little bit higher in energy in terms of its transition state. So it is not the favored approach of the, the molecules, relatively speaking. So we've figured out the the correct alignment, and now we need to figure out, or sort of imagine what's happening with the orbitals in the reaction. Recall that the bond between carbon 1 and carbon 2 undergoes a clockwise rotation. And that starts happening as this becomes sigma bond. Prior to the reaction, it was a double bond, and there was no rotation, right? But as the reaction is occurring, it becomes a sigma bond, and we allow for rotation. So as this occurs, this p orbital morphs into an sp3 hybridized orbital, and the group that's pointed in, which is a hydrogen, ends up, and the group that's pointed out, which is a methyl, ends up down because of the clockwise rotation. You can also play around with models to help you visualize where these groups end up after you do bond rotation. In terms of carbon 3 and carbon 4, we have a counterclockwise rotation, and that's because the bottom lobe needs to point the opposite direction than the one before in order to form a 6-member ring. So as this p orbital morphs into an sp3 hybridized orbital, the methoxy group, which is pointed in, ends up, and the hydrogen ends up down due to the counterclockwise rotation. So in summary, these opposite directionality in terms of carbon-carbon bond rotations lead to the stereochemistry at carbons 1 and 4 as they're labeled here. What's going on with the dienophile, right? We need to draw that in as well and show the primary orbital overlap. Notice that I've placed the electron withdrawing group in an endo position. So as these sigma bonds start to form, this entire molecule starts to rotate counterclockwise, and the groups that are endo end up pointed down, and the groups that are exo end up pointed up. So these endo-pointed groups usually end up down. This is only with a bottom approach. The exact opposite would happen with a top approach. You would end up with those groups pointed up, leading to an enantiomer. So here we can visualize the sigma bonds being formed from the head-to-head overlap of the sp3 hybridized orbitals and all of the stereochemistry that results. And then translate that to the product. So we've got the methyl group pointed down, the methoxy group pointed up, And the electron withdrawing group, which is the methyl ketone, which was pointed endo, will end up down. This is not a meso compound because there's no internal symmetry, and therefore the enantiomer is also produced. The enantiomer is produced from the top approach of the dienophile with respect to the diene. Everything happens and all the rotations happen in exact opposite direction, and we end up with exact mirror image product. Okay, let's go ahead and do a practice problem. Now we're putting everything together, so you can use your handout if you would like to really help me. Remember to work through the steps, step 1, step 2, step 3, and include the stereochemical outcome for the Diels-Alder reaction as well. Go ahead and pause, and then we'll go through it when you are ready. Go ahead and start working through these problems. So the first step is looking to see that my diene is drawn in an S-cis conformation, and it is, so I can move to step 2. Step 2 is looking for an internal plane of symmetry. I'm not finding one, so I do need to consider the relative orientation or the regiochemistry. The charges are going to be the delta negative on the bottom here and the delta positive also on the bottom. So these actually happen to be already properly aligned. That's very convenient for me. So I can just start hexene. I don't need to worry about this carbon because it remains sp2. So I'm just going to go ahead and add that methoxy group. However, I do have a methyl group here, another methyl group here, and this methyl ketone ends up here. And those all become chiral centers. So I need to include that stereochemical information. If I imagine a bottom approach, then these two groups that are pointed out will both end up down. So I'm going to draw those on a dash. And in addition, the methyl ketone will prefer an endo approach, and it will also end up down. And this is not a meso compound, so I'm going to write plus enantiomer. Let's move on to the next one. This one, it looks like I was not given the diene in S-cis conformation. So I need to do a rotation about the central sigma bond. And I also kind of want to rotate it so that it's I'm going to be able to align it nicely with the dienophile. I'm also going to slightly rotate this on the plane. You can do this in one step. If you can visualize it all together, then you can do it together. So note that the methyl group ends up here. It's got these two methyl groups on the interior carbons. So now I'm in an S-cis conformation. And I'm ready to go in terms of considering regiochemistry, which is step 2. I'm looking for an internal plane of symmetry, and I'm not finding one. So I do need to consider the regiochemistry. To do that, I have to figure out where the delta negative and delta positive carbons are. If I draw resonance contributors, I'm going to find that that is delta negative, that is delta positive. And as they're drawn now, we would have an improper alignment. So I am going to need to rotate or flip this dienophile over. So I am going to flip it over so that my nitro group is on the top carbon and not the bottom carbon. That will make the delta positive in alignment with the delta negative. So I can get the proper regiochemistry. I'm going to start sketching in the product by drawing in the cyclohexene ring. My two methyls end up planar, so I don't have to worry about those. But I do have a methoxy group and a nitro group that end up on chiral carbons. Because the methoxy group is pointed in, it's going to end up from a bottom approach. Because the nitro group will also be pointed endo, because it's electron withdrawing and that favorable secondary orbital overlap occurs when the nitro group is endo, it will end up down. This is not a methyl compound. Moving on, so here we have a bicyclic compound. So again, we can practice drawing our bicyclic structures. I do have the cyano groups, which are opposite. So again, one is down and one is out. That is the correct relative stereochemistry. By the way, when you're drawing a bicyclic product, you do not need a dash or a wedge because this tells you the stereochemistry without dash or a wedge. And this is not a methyl compound, so I'm going to write plus. Moving on to D, I'm looking to see that my diene is an S-cis conformation, and it is. So I can move on to step 2. Step 2 is looking for an internal plane of symmetry. I found one in the dienophile, so I don't need to worry about chemistry. But I am going to need to worry about stereochemistry because I see a lot of groups attached to these carbons that are becoming sp3. So what I can do is start to sketch in the product and then worry about adding in dashes and wedges. So remember that these groups are electron withdrawing groups, these ester groups that are part of the ring. So those are going to prefer an endo position. They're going to end up pointed down when I imagine a bottom approach of the dienophile. And the hydrogens here will be in exo positions, so up here. I also have a methoxy group here, which I can add in. And I have a methyl group here, which is pointed out, which means that it will rotate down. And then I have both a methyl and an ethyl group here. Notice that the ethyl group is pointed out, so it will rotate down. And the methyl group is pointed in, so it will rotate up. And I need to write going back to the slides, we are going to move on to the final section of our chapter that we're going to cover, which is 16.8, and talking about a new reaction, a new cycloaddition reaction, and in addition, molecular orbital descriptions are important to understand the reaction. So we're going to be considering what's called a 2+2 cycloaddition. It's not a named reaction because it's not as important as the Diels-Alder reaction. And it's called a 2+2 because we have a 2-pi system reacting with a 2-pi system. If we wanted to get these alkenes close together, we could shift the pi bonds to form new sigma bonds and generate a 4-membered ring. So even though I could draw arrows that would suggest the formation of a 4-membered ring, the question is, does this work, right? Would this reaction work? One thing we can do is use frontier molecular orbital theory to figure out if the HOMO and LUMO would be in proper alignment to allow for a conservation of orbital symmetry. So what I want to do is align the HOMO of one of the alkenes with the LUMO of the other. So the first thing you want to do is just look at the molecular orbitals of a simple alkene. Recall that with an alkene, there's only 2 molecular orbitals. There's the pi bonding and the pi anti-bonding molecular orbital. The HOMO is the pi bonding, and the LUMO is the pi anti-bonding. The HOMO has the 2 electrons in it from the pi bond, and the LUMO does not. But if we're reacting one molecule of ethylene with another molecule of ethylene, one will have to act as the nucleophile and be the electron donor, and it will donate electrons from its HOMO into the other molecule's LUMO. So the other ethylene is then acting as the electrophile, and it's accepting the electrons from the HOMO, and it has to accept them into the LUMO because its HOMO is filled. So we need to see if we align these, the HOMO of one molecule and the LUMO of the other, will we see conservation of orbital symmetry? And the answer is no. This process is what we call symmetry forbidden, because even though one side's orbitals line up or constructive or orbital overlap. The other sides does not line up, and this would lead to destructive interference, which will not lead to a bond, according to bonding theory. So thermally, if we just heat the reaction or mix the two together, we're not going to achieve any cyclobutane. However, it is possible to make cyclobutane via a 2+2 cycloaddition, but only when light is used to excite an electron. Let's remind ourselves what happens when light is shined onto a double bond. So an electron could potentially be promoted if there's the right frequency of light being used that matches this energy gap from the HOMO into the LUMO, which creates what used to be the LUMO is now the new HOMO. This will not happen with both molecules simultaneously. This process is very slow. So only a small percentage of the ethylene in the solution would actually have an electron promoted, an excitation, as we call it, at any given time. So there would be plenty of ethylene around that's in its ground state. So only a small percentage of ethylene would be in its, what we call its excited state, and a large percentage of ethylene would be in its ground state. But now we have a possible interaction between the new HOMO, the excited state of ethylene, and the LUMO of another molecule that's in its ground state. And when we look and see if the HOMO in the excited state of one molecule lines up with the LUMO in the ground state of another molecule, we'll see that we do have a symmetry allowed process. And so we can synthesize cyclobutane. So if you mix ethylene in the presence of light, right, you can actually achieve cyclobutane through a 2+2 cycloaddition. However, if light is not present, then no reaction occurs. And that is the power of molecular orbital theory, that it allows for these predictions before we even do any reactions, and then we can match up our predictions with what we actually see in the laboratory. Let's consider a final problem. Consider the following 4+4 cycloaddition process. Would you expect this reaction to occur through a thermal or a photochemical pathway, basically by heating or by using light? Use frontier molecular orbital theory to justify your explanation. And I went ahead and added in the molecular orbitals for butadiene because you're going to need those if you're reacting two molecules of butadiene to potentially form cyclooctane. Go ahead and pause it and try to align HOMO and LUMO to see if it would be possible thermally or with after a light excitation. When you're ready, you can go over it. Okay, let's go ahead and go. So technically, we can draw arrows that would suggest that this reaction will take place. I can shift these pi electrons, form a signal bond between those two carbons, simultaneously shift all the electrons in a ring, so cyclic transition state. And oops, sorry, I forgot the pi bond. You were not too confused by that, but it's a question of would this be possible to form this? Even though I can draw arrows, I don't know if it's going to be thermally allowed or possibly allowed. Okay, let's go ahead and draw in the HOMO and the LUMO of both of these molecules. So I'm just going to kind of draw one approaching the other from the bottom. And then I can draw in a bunch of p orbitals. Right? And again, we want to use the HOMO of one and the LUMO of the other. So we're going to say HOMO of one butadiene, the LUMO of another butadiene. So in the HOMO, I have a node right in the center. And in the LUMO, I have a node in between carbons 1 and 2 and 3 and 4. So my nodes will be here. So that's where I know when I should change the phase. Okay, so as I'm drawing this, I'm going to try to use blue and red, have here, and I'm going to start drawing in the HOMO. Blue, blue, flip the sign, the blue is now top. So now I've drawn in the HOMO, basically this one, right, drawn in right over here. And then I'm going to try to align that with the LUMO of another molecule. So again, I'm going to put the blue on the top here so that it can nicely overlap. And that means I have to flip the blue to the bottom over this node, go on the bottom again, and then flip again for the second node. Let's join the red nodes. Here's the bottom, top, top, and what I found out is, although I do have nice alignment on one side, when I look for alignment on the other side, it doesn't work out, right? Blue cannot align with red. That is not constructive interference. That is destructive. It will not lead to a bond. So it does not work thermally, right? So we can just write not thermally allowed. What about, would it be allowed photochemically? Say this is, what is the terminology? Symmetry forbidden. Technical term. Okay, so recall that if we use light, we can promote an electron, right, to a higher energy level, and this would now become the new HOMO. And it would interact with the LUMO of another molecule in its ground state. We're going to go ahead and try to draw the same sort of picture here, where I am drawing in two 23 butadiene. And again, I'm going to use the HOMO now in an excited state. So I should have written these are both ground state. HOMO, ground state. So now this is going to be HOMO in the excited state, interacting with molecules LUMO in the ground state. And that's because, of course, only a small percentage of molecules will be excited. The likelihood that it interacts with another excited molecule is very low. Okay, so the HOMO in the excited state is this orbital, and it's also the LUMO in the ground state. So essentially the same. You go and nodes, fine. Start with blue. I'm just going to draw down, up, up, down. It doesn't matter which way you flip it over, the opposite. And then red, draw the other lobe. And then because I want these to align, I'm going to start with blue on top, below, on top. Now when I check for alignment, what I can see is that they are both going to have a constructive interference. So this is a symmetry allowed process. So this reaction is possible, but is only possible if you have the right light source to be able to promote an electron from the HOMO to LUMO to get an excited state molecule. Okay, so we are done with the lecture. Hopefully you have enough information that you can tackle the activities this week. As always, come see me in office hours. I would love to answer any questions and clear up any misconceptions that we may